Section: Introduction. We're going to talk about a common problem with advanced language learning models, LLMs. Despite their sophistication, they often struggle with factual errors. One way to address this is through Retrieval-Augmented Generation, RAG, methods. These methods enhance the input of LLMs with relevant information from retrieved passages, which can help reduce factual errors. However, these methods aren't perfect. They can sometimes limit the versatility of LLMs or introduce irrelevant or off-topic passages, leading to lower quality outputs. To address these issues, we're introducing a new approach called Self-Reflective Retrieval-Augmented Generation, SELF-RAG. This method aims to improve the quality of an LLM's output, including its factual accuracy, without compromising its versatility. It does this through on-demand retrieval and self-reflection. Here's how it works. We train a language model to reflect on its own generation process. It does this by generating both the task output and special tokens, which we call reflection tokens. These tokens are divided into retrieval and critique tokens. Retrieval tokens indicate when retrieval is needed, and critique tokens assess the quality of the generation. When given an input prompt and preceding generations, SELF-RAG first determines if augmenting the continued generation with retrieved passages would be helpful. If it would be, it outputs a retrieval token that calls a retriever model on demand. Then, SELF-RAG processes multiple retrieved passages, evaluates their relevance, and generates corresponding task outputs. It also generates critique tokens to assess its own output and choose the best one in terms of factuality and overall quality. This process is different from conventional RAG methods, which always retrieve a fixed number of documents for generation, regardless of whether retrieval is necessary. SELF-RAG also provides citations for each segment with its self-assessment of whether the output is supported by the passage, making fact verification easier. We train our generator language model on a diverse collection of text interleaved with reflection tokens and retrieved passages. The reflection tokens, inspired by reward models used in reinforcement learning, are inserted offline into the original corpus by a trained Critic model. This eliminates the need to host a Critic model during training, reducing overhead. Our trained language model uses critique tokens to assess its own predictions after each generated segment. This is an integral part of the generation output. SELF-RAG also enables a customizable decoding algorithm to satisfy hard or soft constraints, which are defined by reflection token predictions. Our empirical results on 6 tasks, including reasoning and long-form generation, show that SELF-RAG significantly outperforms pre-trained and instruction-tuned LLMs that have more parameters and widely adopted RAG approaches with higher citation accuracy. In terms of related work, Retrieval-Augmented Generation, RAG, has been used to augment the input space of LLMs with retrieved text passages, leading to large improvements in knowledge-intensive tasks. However, these methods often retrieve only once at the beginning and may not be as efficient or robust as our method. A few concurrent works on RAG propose new training or prompting strategies to improve widely adopted RAG approaches. While we also train our model on diverse instruction following datasets, SELF-RAG enables retrieval on demand and selection of the best possible model output via fine-grained self-reflection, making it widely applicable and more robust and controllable. Training LLMs with reinforcement learning from human feedback has proven effective in aligning LLMs with human preferences. However, our method trains our target LM on task examples augmented with reflection tokens from a Critic model offline, with a far lower training cost compared to reinforcement learning from human feedback. In conclusion, SELF-RAG uses reflection tokens to decide the need for retrieval and to self-evaluate generation quality. This approach is different from other methods that focus only on reasoning tasks with one evaluation dimension and without retrieval. Our method enables controllable generation at inference, while other methods focus on human preference alignment during training. Section Summary. State-of-the-art language models, LLMs, often struggle with factual errors, even with increased model and data scale. Retrieval-Augmented Generation, RAG, methods have been used to reduce these errors by augmenting LLM inputs with relevant retrieved passages. However, these methods can hinder versatility and introduce unnecessary or off-topic passages. This work introduces self-reflective retrieval-augmented generation, SELF-RAG, which improves an LLM's generation quality and factual accuracy by using on-demand retrieval and self-reflection. Section: Self-RAG. Learning to retrieve, generate, and critique. We're introducing a new framework called Self-Reflective Retrieval-Augmented Generation, or Self-RAG for short. This framework improves the quality and accuracy of a language model, without compromising its original creativity and versatility. Our approach involves training the language model to generate text based on retrieved passages, and then critique its own output by generating special tokens. These tokens indicate whether retrieval is necessary or confirm the relevance, support, or completeness of the output. This is different from typical retrieval-augmented generation (RAG) methods, which retrieve passages without ensuring full support from the cited sources. To explain this in more detail, let's consider an input, X. We train the language model to generate textual outputs, Y, in a sequential manner. These outputs consist of multiple segments, each represented by a sequence of tokens. These tokens include text from the original vocabulary as well as the special reflection tokens. During the inference process, for every input, X, and preceding generation, the model decodes a retrieval token to assess the need for retrieval. If retrieval isn't necessary, the model predicts the next output segment as a standard language model would. If retrieval is needed, the model generates a critique token to evaluate the relevance of the retrieved passage, the next response segment, and another critique token to assess if the information in the response segment is supported by the passage. Finally, a new critique token evaluates the overall utility of the response. To generate each segment, Self-RAG processes multiple passages in parallel and uses its own generated reflection tokens to enforce constraints over the generated task output. For example, in one scenario, the model selects the first retrieved passage because the second one doesn't provide direct evidence and the third one is only partially supported, while the first one is fully supported. In terms of training, Self-RAG allows any language model to generate text with reflection tokens by treating them as next token predictions from the expanded model vocabulary. We train the generator model on a curated corpus with interleaving passages retrieved by a retriever and reflection tokens predicted by a critic model. We train the critic model to generate reflection tokens for evaluating retrieved passages and the quality of a given task output. Using the critic model, we update the training corpus by inserting reflection tokens into task outputs offline. Then, we train the final generator model using the conventional language model objective to enable it to generate reflection tokens by itself without relying on the critic at inference time. We also describe the supervised data collection and training of two models, the critic and the generator. Training the critic model involves data collection, which can be expensive if done manually. To overcome this, we use a state-of-the-art language model like GPT-4 to generate feedback. However, relying on such models can increase costs and reduce reproducibility. So, we create supervised data by prompting GPT-4 to generate reflection tokens and then distill their knowledge into our own critic model. For each group of reflection tokens, we randomly sample instances from the original training data. We use different instruction prompts for different reflection token groups. For example, we prompt GPT-4 with a type-specific instruction followed by few-shot demonstrations, the original task input, and output to predict an appropriate reflection token as text. Manual assessment reveals that GPT-4 reflection token predictions show high agreement with human evaluations. We collect 4K20K supervised training data for each type and combine them to form training data for the critic model. Section Summary. The paper introduces a framework called Self-RAG, which enhances the quality and factuality of a language model, LLM, through retrieval and self-reflection. It allows the LLM to generate text informed by retrieved passages and criticize the output using special tokens that signal the need for retrieval or confirm the output's relevance, support, or completeness. The framework also includes an inference overview and a training overview, which involve decoding retrieval tokens, generating critique tokens, and training the generator and critic models. Section: Critic Learning. We begin by teaching our critic model. After gathering the necessary training data, we start with a pre-trained language model, LM, and train it on this data. The goal is to maximize the likelihood, a common objective in conditional language modeling. We use the same pre-trained LM as the generator for initializing the critic model. This critic model shows over 90% agreement with predictions based on GPT-4 for most reflection token categories. Next, we train the generator model. We start by collecting data for the generator. Given an input-output pair, we enhance the original output using the retrieval and critic models. This creates supervised data that closely mirrors the process used during inference. For each segment of the output, we use the critic model to determine if additional passages could improve the generation. If retrieval is needed, a special token indicating retrieval is added, and the retrieval model fetches the top passages. The critic model then assesses the relevance of each passage and predicts whether the passage supports the model's generation. Tokens indicating relevance and support are added after the retrieved passage or generations. Finally, the critic model predicts the overall utility token, and the augmented output with reflection tokens and the original input pair is added to the generator's training data. We then train the generator model on this curated corpus, which now includes reflection tokens. Unlike the critic model, the generator model learns to predict both the target output and the reflection tokens. During training, we mask out the retrieved text chunks for loss calculation and expand the original vocabulary with a set of reflection tokens. Our approach is similar to recent work that incorporates additional feedback during training. However, instead of relying on separate reward models during training, we compute critique offline and directly insert them into the training corpus. This significantly reduces training costs. Our model also learns to generate special tokens to evaluate its own prediction after each generated segment, enabling the use of a soft re-ranking mechanism or hard constraints at inference. During the inference phase, our model generates reflection tokens to self-evaluate its own output. This makes the model controllable and allows it to adapt its behavior to different task requirements. For tasks requiring factual accuracy, the model retrieves passages more frequently to ensure that the output aligns closely with the available evidence. Conversely, for more open-ended tasks, the emphasis shifts towards retrieving less and prioritizing the overall creativity or utility score. Our model can also adaptively retrieve text passages by predicting a special retrieval token. Alternatively, a threshold can be set. If the probability of generating the retrieval token surpasses a designated threshold, we trigger retrieval. At each segment step, when retrieval is required, the retrieval model fetches multiple passages, and the generator model processes each passage in parallel and outputs different continuation candidates. We conduct a segment-level beam search to obtain the top segment continuations at each timestamp and return the best sequence at the end of generation. The score of each segment with respect to a passage is updated with a critic score, which is the linear weighted sum of the normalized probability of each critique token type. The weights in this equation are hyperparameters that can be adjusted at inference time to enable customized behaviors. For instance, to ensure that the result is mostly supported by evidence, we can set a weight term for the support score higher, while relatively lowering weights for other aspects. Alternatively, we could enforce hard constraints during decoding using critique tokens. Instead of using a soft reward function, we could explicitly filter out a segment continuation when the model generates an undesirable critique token. Balancing the trade-off between multiple preferences has been studied in reinforcement learning with human feedback, which often requires training to change models' behaviors. Our model tailors a language model with no additional training. Section Summary. In this section, the authors describe the process of training the critic model and the generator model in the self-RAG framework. The critic model is initialized with a pre-trained language model and trained on a dataset of generated outputs to assess the relevance and support of passages. The generator model is trained on a curated corpus augmented with reflection tokens, and it learns to predict the target output as well as the reflection tokens. During inference, self-RAG can dynamically decide when to retrieve text passages and use tree decoding with critique tokens to control the generation process based on different objectives. Section: Tasks and Datasets. We've carried out a comprehensive evaluation of our model, self-RAG, and various other models on a variety of tasks. We've used metrics that measure overall accuracy, factual correctness, and fluency of the output. We've performed these evaluations without any prior examples or demonstrations, a method known as zero-shot evaluations. You can find more details about our experimental setup in the appendix. We've used two types of tasks for our evaluations. The first type, closed-set tasks, includes a fact-checking dataset about public health and a multiple-choice reasoning dataset derived from scientific exams. We've used accuracy as the measure of performance for these tasks. The second type, short-form generation tasks, includes 2 question-answering datasets where the model has to answer random questions about factual knowledge. We've used a subset of one of these datasets that includes rare entity queries. We've also used a dataset for which the test set is not publicly available, so we've followed the same validation and test split as previous research. We've also evaluated long-form generation tasks, which include a biography generation task and a long-form question-answering task. We've used a metric called fact score to evaluate the biographies, and official metrics of correctness, fluency, and citation precision and recall for the question-answering task. We've compared our model with several other models. Some of these models don't use retrieval, including pre-trained language models, models tuned with instructions, and models trained with private data. We've also compared our model with a model that uses iterative prompt engineering to improve factual correctness. We've also evaluated models that use retrieval either during testing or training. This includes standard models where the output is generated based on the query in the top retrieved documents, and models where the language model is fine-tuned on all the training data we use. We've also evaluated models that use retrieval and are trained with private data, as well as a production search system based on Instruct-GPT. Our training data consists of a variety of input-output pairs that follow instructions. We've used 150,000 of these pairs for our training. We've used 2 versions of a language model called Llama 2 as our base language model, and we've used an off-the-shelf model called Contriever-MS Marco to retrieve up to 10 documents for each input. For our testing, we've assigned certain weight terms values of 1.0, 1.0, and 0.5. We've set the retrieval threshold to 0.2 for most tasks and to 0 for one task due to citation requirements. We've used a method called VLLM to speed up testing. We've used a beam width of 2 for each segment level and greedy decoding for token level generation. We've used the top 5 documents from Contriever-MS Marco by default, and for certain tasks, we've used additional documents retrieved by a web search engine. Section Summary. The section discusses the tasks and datasets used for evaluation in the paper. The authors conduct evaluations on various downstream tasks, including fact verification, multiple choice reasoning, short-form generation, question answering, and long-form generation, biography generation and long-form question answering. They compare their method, self-RAG, with diverse baselines, including instruction-tuned models and models trained with private data. The evaluation metrics used include accuracy, fact score, fluency, and citation precision and recall. Retrieval-based baselines and concurrent methods trained with retrieved text passages are also evaluated. Section: Main Results. Let's delve into the main findings of our study. We'll start by comparing our model, self-RAG, with other baseline models that don't use retrieval. The results, as shown in the top part of the table, indicate that self-RAG significantly outperforms other models that have been fine-tuned using supervised learning. This is true across all tasks, and our model even surpasses ChatGPT in areas such as public health, popular question answering, biography generation, and ASQA. Interestingly, our model also outperforms a concurrent method that uses complex prompt engineering. For instance, in the task of biography generation, our 7B and 13B models outdo the concurrent Cove model, which uses an iterative prompting approach to refine output. Next, we compared self-RAG with baseline models that do use retrieval. The results, shown in the bottom part of the table, reveal that our model outperforms existing retrieval-augmented models in many tasks. In fact, it achieves the best performance among all non-proprietary language models across all tasks. While our model outperforms other baselines in popular question answering and biography generation, we found that models that are fine-tuned with powerful instructions and use retrieval, such as Llama 2 Chat and Alpaca, show significant improvements over their non-retrieval counterparts. However, these models offer limited solutions for tasks where we can't simply copy or extract parts of retrieved passages. For example, in public health and ARC challenge tasks, retrieval-based models don't show a notable improvement over their non-retrieval counterparts. We also found that most retrieval-based models struggle to improve citation accuracy. However, our model shows significantly higher citation precision and recall than all models except ChatGPT. We also conducted a series of ablation studies to identify the key factors contributing to our model's performance. We evaluated two model variants that were trained differently than our model, one without a retriever and one without a critic. The results show that all components play important roles, and there is a large performance gap between self-RAG and the models without a retriever or critic. This indicates that training a language model with these models significantly contributes to the performance gain of self-RAG. One of the key benefits of our framework is that it allows us to control how much each critique type affects the final generation sampling. We analyzed the effects of different parameter weights on our 7B model during inference time on ASQA. The results show that increasing the weight leads to positive effects on the model's citation precision, but it results in lower MAV scores. We also evaluated how the adaptive threshold affects overall accuracy and frequency of retrieval. The results show that the model's retrieval frequencies dramatically change as the threshold varies. On one hand, performance deterioration by retrieving less is smaller on public health but larger in popular question answering. We also analyzed how the size of the training data affects the model's performance. The results show that increasing data size often leads to improvements, especially in popular question answering and ASQA. However, we didn't observe such significant improvements when increasing the training data from 50K to 150K. Finally, we conducted small human evaluations on self-RAG outputs. The results show that human annotators often find self-RAG answers to be plausible and supported by relevant passages. They also find that the model's predictions about relevance and support match their assessments.